Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. In the last class, we talked about various governing equations. Particularly, we talked about the steady-state heat connection problem. We also talked about taut string problem of one dimension. And similarly, we talked about two dimensions. So, and then we also talked about something about the torsion of non-circular cross-section. And there's another important class of problems, like the solid mechanics problems, which I mentioned earlier. They're a little bit more complex, and the number of equations involved are a lot more. And then we will take it up separately a little later. And before that, we will let's continue to talk about the equations, which are much simpler, like the heat connection problem, which is just a one variable problem, or even membrane, which is a one variable problem. And then let's talk about various methodologies involved, and then how they can all be implemented in the finite element methodology. And so till now, we're talking about a problem, a physical problem, converted into mathematical equations. And in particular, we talked about differential equations, which means that the variables are supposed to satisfy a certain differential equation at each and every point in the domain, together with the boundary conditions, of course. So apart from that, there is another way of defining the problem is the variational approach. Variational this I call it as a second one. The first one was the differential equation way of formulating the problem. And now let's look at the variational formulation. What we are saying here is that there is a second way of defining the problem from the physics to the mathematics. That is the variation formulation, which is a very popular kind of formalizing, and which has been there for many, many centuries, Rayleigh time. In this variational formulation, so what we have is we define it in such a manner, so where we will obtain the solution as a minimization or a maximization of a certain quantity. Let's illustrate it with respect to a simple problem of the string. So let's take a string problem. So this, as I was saying, so this involves the minimization or maximization of a certain quantity. And then we will just see how it is related to the actual solution. So let's take the example of a one-dimensional taut string. So in this one-dimensional string, we know that the string is stretched between 2 points, A and B, and of course, X is the direction. And of course, this is inside. It is under tension T, and then we have a load which is laterally applied, and under the action of this one, so the beam or this string, is going to undergo a deflection, and the deflection we denote by W. So here the deflection is W, which is a function of X. So this is the one which we are trying to obtain. So the deflection as a function of X is our goal. Given the length of the string L here, length of the string L, and then this is under tension T, as well as an applied load Q that's given to us. So earlier we defined certain differential equations. So like d square W by dx square plus Q, so that is Q by T, so that's equal to 0. So that's how we defined it. But now the same problem, we are going to formulate it in a different manner. Okay. And so how we are going to formulate it is that using the potential energy. So we will we'll define a potential energy. This is the classical formulation wherein we say that a system will attain a minimum potential energy. Of course, there are certain conditions and all that which I defined here. So a system which is loaded by certain forces and maybe under gravity or maybe under different kinds of loads. So we'll try to attain a minimum potential energy configuration. So we will just see it. So let us say, so that means that we will call this quantity as pi. So what is this pi? So pi is going to be a function of W itself. So if W is like this one, and then there may be, for example, there may be another W here, and another W here. So if this is the actual solution, W bar, and let us say this is W1 and W2. So all these things, of course, are functions of X. So for W1 and W2, so each configuration is associated with a certain potential energy. What is that potential energy due to? One is the load which is being applied here laterally is moving through different vertical deflections. So that means that the potential energy due to Q has moved by actual W, and then or W1 or W2, which are also functions of X. So the potential energy associated with Q will be different. As well as there is also another potential energy term is associated with the string. So the string here is of a certain length here. Originally it is of length L, but under deflection, so it is going to have certain different lengths, and then it will have different internal energy. So the total potential energy of the system is due to the elastic energy in the string increase in, for example, if you take this to be having, to start with, it is having 0 value. Okay, you can always take datum anywhere. So if it is having a 0 potential energy, so all these things, the string is going to extend its length, so its internal energy is going to increase. So its potential energy is going to increase. On the other hand, we also have another agent here, that is the Q. So Q also is moving through different deflections, so it will also contribute to different potential energies. So these two put together will constitute the total potential energy of the system. Okay. So let us see, first of all, let us see how we can calculate the potential energy. Okay. So the potential energy we are going to calculate to start with. The potential energy is due to, I'll write it here, is due to increase in length of string. This is number one. And the other quantity is also due to the movement of, let us say force, but let us simply write it of load Q. Okay, so these are the two counteracting agents which will change the potential energy. So let's look at the potential energy due to the increase in length. So let's just look at in a positive sense. Elastic energy of string is, let's talk about, this is x-axis, and let us just say that so here we have a delta x to start with, and then we have this string has changed its length to delta s. Okay, and so the initially this part of the segment is subjected to a tension T, and obviously the tension will not change, will continue to be the same because the deflections are small. But however, the elastic energy is changing because the T which is acting on delta x now has changed to T acting on delta s, which is this length. So obviously a string which is of this length, now if it has increased to a value of delta s, so that means that there is an increase in energy of the string. Okay. So how much is that? So here, since T is constant, so T multiplied by the change in length will give you the change in the, if you call it as work done, or the energy in the system has increased. So let us just see how much is that. So what is the new distance delta s? So again, I recall you. So now I am following a positive sign convention here. So this is a positive sign convention. In the sense that everything in the positive direction are considered to be positive, in the sense that the deflection of the string is in the positive direction. Okay, and so that's what it is. And here this is W, and so W is here. W in the upward direction is considered to be positive here. W is a function, deflection, so deflection we call it upward as positive. So let us just see here the new change. So the original length here of this segment is delta x, and change length is delta s. And how much is delta s? So let us just see. So the difference is delta s minus delta x, and the work done by T is equal to T times. So this is the additional energy that has gone into the system. So T has increased by so much and so on. So what is delta S here? So delta S is, this is delta X, and this is W, and then the increase in this vertical deflection is W plus delta W. So this small piece is delta W, and so delta S can be written as delta X square plus delta W square, which we can write it as delta X we can write it like this. And if you write it as 1 plus to the power of half here, right? And so the 1 in the bracket, so this plus this square to the power of half here can be written as 1 plus half delta W by delta X square. And then there will be more terms here using binomial expansion. So it's 1 by 8 delta W by delta X to the power of 4 and on and on. So which can be now taking the dominant terms. So forget about these terms. So we'll take two terms. So this is approximately this one. This is because the term, if you go into the limit, so this delta W by delta X, which go into the limit, we'll write as dW by dx, is very small compared to value 1. Okay, so this slope dW by dx is nothing but the slope of the string. So the string is essentially horizontal, and it's going to be a very, very small value. Okay, so if this is so, then I will just write it here. I will write it as dW by dx square here. All right, so now substituting this into this equation, so the elastic energy or work done by T is change in elastic energy, T into is nothing but delta X 1 plus half dW by dx square, and this delta S part, and this is delta X, right? So which will turn out to be T times half okay. So this is how the increase in the elastic energy in the string. Okay, apart from this, we also said that there will be a change in energy of the total system because of the load acting Q here. So there is a Q acting here. What is Q? So Q is due to the load Q. So the work done here is something like here. what is the work done by Q here? So the load Q here, Q times delta X is the load, and then there is the whole load has moved through a distance of W here. Okay, so this is the work done by external load, and then this is as far as the potential energy is concerned, the potential energy change is minus. So whenever there is an external force, if it is acted through a distance W, so we say that Q into delta X, so this is the total load multiplied by W. So this is the distance through which it's moved with a negative sign, because there is a loss in potential energy. Something like if you have a load here which is acted upon by its own weight, there's a body which is acted upon by its own weight. So if it moves through in the same direction as the weight, then we call it as it has lost its potential energy. So this you understand. So the same way here, that if the Q is moving in the direction of the W, so then it will lose its potential energy. So now what we finally have is that what we have here is the change in potential energy is, or the potential energy of segment of delta X is nothing but T times half multiplied by dW by dx square delta X minus Q times delta X times W. So this is the for this segment, the delta X. So then the total potential energy of the system is given by an integral of this one 0 to L of T by 2 dW by dx square minus Q times W times dx. So this we represent as a pi, and this is the total potential energy. The principle here is that, as I was telling you, that so if you look at different configurations here, W1, W2, W3, here different configurations, then these are all called approximation. So we do not know which one is the right one, W1 or W2 or W3, right? So W1, W3, so we'll call it as W hat. So this is the approximation. We do not know which is the right one. So we have an approximation here, which is a function of x. So what we are saying here is that pi here, if you substitute W hat, so you can even say it's a pi hat. So pi hat is going to have different values depending upon the W hat. The principle here is that out of all these W hats, different configurations, if you take W1, W2, W3, different values. So then out of all these approximations. For each approximation, you can calculate the potential energy pi. And the principle here is that out of all these different approximations, the one which gives you the lowest potential energy is the solution of the problem. So what we say here, so the one function W hat which gives the lowest potential energy, W pi hat, is the solution of the problem. So this is the interesting part here. Of course, there is a precondition on this one, which also is that the precondition is that all W hats here satisfy the end conditions, boundary conditions. In fact, I should modify this statement saying that out of all W hats which satisfy the boundary conditions here, what is the boundary condition here? So that is W is equal to 0 here, and W is equal to 0 at the x is equal to L. So these are the two boundary conditions. So out of all these W hats which satisfy the boundary conditions, the one which gives you the lowest potential energy is the solution of the problem. So what do we mean by this one? In fact, we have posed this problem, this string problem, in two ways. Earlier also we have posed this problem in a differential equation form. So that is d square W by dx square plus q is equal to 0. So that was the governing equation in the form of a differential equation. Now what we have done here is that we formulated it in the variational form, where we formulated a potential energy here, and then we said that the W hat which leads to the lowest potential energy is the solution. Whether you solve the differential equation and get the solution, obviously you can do that, or whether you assume a number of approximations here and out of which you choose the one W hat which leads to the lowest potential energy. So both these approaches will give you the same solution. So this is you can also say that the one which minimizes the potential energy by hat, okay, will satisfy the differential equation. Or you can also say that the equation which satisfies the differential equation is the one which minimizes the potential energy. So both ways you can say that. So remember, this W hats which satisfy the boundary conditions, these are called admissible functions. And another small thing here, this pi hat here, which we call as the potential energy. So this pi hat is what? Pi hat is actually a function of W hat. So that means that putting these different W hats, we are going to have different values for pi hat. So pi hat is a function of W hat, and then this is a function of function. So this is a function for different W hats. You are going to have different values. So this is called also a functional. So pi hat is also known as a functional, where because pi hat is a function of function. Okay. So like this, so out of all admissible functions, the one W hat which minimizes this functional is the solution of the problem. So this is how we either formulate it as a governing equation or a variational formulation. So the advantage of this variational formulation quite often this variational formulation gives us a feel, a physical feel of the problem. So this is not very abstract. So we are exposed to this minimum potential energy of the systems, and this will give you a feel for the problem. So that's why many times this potential energy approach or the variational energy approach is quite feeling. Okay. So in our course, we are going to obtain the approximate solutions by this method as well as directly by differential equations method also. So there is another small thing here is then there is a third approach here, which probably, so this is the second approach, which is a variational formulation. There is a third approach, the principle of virtual work. So this is another third approach. So this is essentially for our solid mechanics problems or the structural mechanics problems, where if this is the solution, okay, and if this is a solution for U or V, U bar, and the idea here is that if you perturb a solution U bar by a small value here, so this is called a virtual displacement. So if you give a virtual displacement to the equilibrating solution, so then the work associated with this, the displacement, virtual displacement is zero. So this is again another very beautiful principle, which we are going to take it up when we talk about solid mechanics problems. So essentially, so thus we have three approaches. One is the direct differential equation approach. The second one is the variational approach. The third one is the principle of virtual work, which is a very powerful one, which we will talk up later. For the moment, I think we'll close at this point, and tomorrow we'll go into some of the solution procedures to obtain the solution. Bye-bye.